All right, good afternoon everybody. I'm Max, I'm a PhD student from the University of Adelaide, which means it only took me 30 hours to get from my home to Dijon. But it's great to be here, and I think it was worth the trip. So I'll be talking today about simulating Twitter hashtag networks. To provide some necessary background, most of my PhD work focuses on community detection and graph labeling, particularly in social networks, predominantly Twitter data, but also generally co-occurrence networks. Previously, in the course of my research, I've developed a new community detection method, because obviously there's not enough of those yet, where we model generally an undirected weighted graph as a discrete time Markov chain. So the edge weights in your graph would inform the transition probabilities in your Markov chain. And the idea is that generally you might know some community information, or you might know some labels for the nodes in your graph, and you could treat those nodes as absorbing states in your chain, and then simulate random walks, or in fact exactly calculate the absorption probabilities for all of the unlabeled walks or unlabeled nodes in your graph to get a sort of probabilistic estimate of community membership for your graph in total. And in that sense, it sort of means that GLASS detects community structure using weighted degree distribution. So if you can find a subgraph of nodes who have a fairly high sort of mean weighted degree within the subgraph, compared to the weighted degree to all of the nodes outside of that subgraph, GLASS is likely to identify that as a community. And as a starting point, we did validate GLASS empirically on a fairly limited class of networks looking at American political voting data. So it's a co-occurrence network where we look at how often politicians in America vote the same way on particular legislation. And we use this as a way to estimate their party affiliation as either Democrat or Republican. But obviously this is a very small class of graphs, so we need to sort of validate it more properly with a simulation study, throw it at a really large set of graphs and see where it performs well, where it falls down. And we've tried some existing models, but we think there are a couple of limitations that mean that maybe a new generative model might be warranted. So the first thing we looked at was a weighted stochastic block model. So effectively you're simulating a graph with a set of blocks where each block is itself a cluster or a community. And you can think of these blocks really as sort of a weighted Erdős-Rényi random graph. And one of the advantages of this model is that you have a good deal of control over both the density and the edge weight distribution within each of these blocks. So you can vary that level of connectivity. You can also vary the connectivity between blocks, sort of mirroring the idea that sometimes there'll be fairly close communities and sometimes communities will be far apart, and we'd like to represent that in terms of how well they connect in the simulated graph. But it's not a perfect approach. We don't have preferential attachment, which we often desire quite greatly. It's not uncommon to have sort of significant hubs within your graph or significant hubs within particular communities, which have incredibly high degree distribution, or sorry, incredibly high degree. We can't guarantee parametrically that we get that with a block model. So we also looked at Lfr Benchmark Networks because they're incredibly popular. And they do have some benefits. Right off the bat, you get more realistic characteristics. You get sort of power law distributions governing things like your degree and community size, which is nice. But there's no inbuilt mechanism to add edge weights, which is something that GLASS sort of likes quite a lot. And it also has a fixed mixing parameter, which means that the connectivity that you get between the communities that you're simulating tends to be fairly uniform, like a level of background noise. So you don't effectively capture this idea where some communities can connect to each other more strongly. And it's not to say that either of these approaches can't be sort of modified or improved, but if you're performing a simulation study, my sense is that it's best to explore as fully as you can the parameter space that underpins your simulation model. And so particularly when you're trying to improve these models by adding preferential attachment in a block model or by adding the edge weights while respecting the degree distribution for your nodes in LFR, your parameter space gets very big, which makes it incredibly time consuming, if nothing else, to properly explore that parameter space. So we've instead thought about a generative model, which is motivated very much by Twitter hashtag networks. So our model aims to sort of take the best of both worlds. We'd like to have this fine level of control over the edge weights and over the density that we have both within and between communities. But we'd also like to have that preferential attachment, this idea that we've got these hubs or these key nodes within our graph or within our clusters where we have a high level of connectivity to those nodes. And also, if we desire it, obviously not every network is scale-free, but certainly a lot of them are. And we'd like to be able to simulate these scale-free networks if we can, which we obviously can't do effectively with a weighted stochastic block model. So as a motivating example, I said I work with Twitter data a lot. If this doesn't make sense to you, don't worry, it didn't make sense to anybody in Australia either. Back in 2017, our government conducted a postal survey because the best way to communicate in 2017 is to send letters to determine the level of public support for same-sex marriage. And this, unsurprisingly, generated a fairly large amount of discussion on Twitter, so there were fairly strong vote yes and vote no campaigns. So around this, we collected about 80,000 tweets, and those tweets contained about 6,000 unique hashtags. We want to analyse the sentiment behind those hashtags. You could consider that vote yes is very obviously a strong positive sentiment, vote no is a very strong negative sentiment, but there are a whole range of other hashtags within that network that maybe sort of aren't absolute yes. They may be like the, oh yes, if certain conditions are met, or you might have a hashtag that's like no, but if these certain conditions are met, I might be more favourable to it. And within the context of the analysis that we run, we're sort of getting these probabilistic estimates of community membership in either pro same-sex marriage or anti-same-sex marriage, where sort of the community membership that probability measures the sentiment of the hashtag itself. And so we want to be able to generate a graph that looks like our hashtag network. So we can start sort of as an overview. We want a set of hashtags, or I guess our nodes. We also want a separate set of our tweets, which we can call containers here. And our goal is to produce, and this is where most of the work of the algorithm comes in, to produce a bipartite graph of U and V, so a graph of our nodes and our containers. So the idea is that edges within our graph would connect nodes to containers. So if a container, that is a tweet, happens to contain a particular node, a hashtag, you draw an edge between them. And then our goal is to project that graph back down over our set of nodes, over our set of hashtags, so that we have this co-occurrence edge-weighted network of hashtags, where we can see, there's an edge between two hashtags if they ever occur in a tweet together, and the edge weight records how frequently they occur. So we'd start by thinking about what our set of nodes has to look like, what our set of hashtags has to look like. And so we consider maybe m+1 nodes that are spaced uniformly on the interval 0, 1. So they're indexed by sort of fractions, woohoo. So we start at 0, which would be an absolute negative sentiment. 1 on m is still pretty negative, 2 on m, still pretty negative, eventually up to 1, which would be absolute positive. So I guess we could have hashtag vote no at one end, hashtag vote yes at the other, and then we've got these intermediate hashtags in between, like hashtag love is love, or hashtag 1M, 1F, which I assume is one male, one female. Again, these are people who maybe think, well, yes, I like the idea of same-sex marriage, but no, I don't want them to get married in churches. Or no, I'm against same-sex marriage, but civil partnerships are okay. So it's expressing this sort of varied, or this spectrum of sentiment between absolute no and absolute yes. We also need to think about what our containers, or what our tweets would look like. So we'd have our set V of containers, and we sort of crudely assign each container to one of two communities in this case. You can do it for more communities, but it gets a little bit gross. So if our tweets are containers, a tweet can contain multiple hashtags, but within this context, we sort of force a dichotomy. So the survey that every person in Australia received wasn't, hey, give us a really detailed overview of how you feel about this issue. It was just tick a box for yes or tick a box for no and post it back. So even though you might have sort of a nuanced understanding or a nuanced sort of take on the issue, ultimately you have to decide whether that pushes you to the yes group or the no group, and we classify all of our containers accordingly. Then we need to think about how many hashtags we'd like to squeeze into each tweet. And this doesn't have to be uniform across the whole data set that we simulate. Some communities we might find tend to group a lot of hashtags into their tweets, and some communities may be sort of less hashtag happy. They might have a lower level of hashtags included. And so we simulate this using a +1+2 distribution. We use +1+2 because we need, in the worst case, every container to contain at least 2 hashtags. Otherwise, we don't contribute any edge information to the projection of our graph. So now we need to figure out how we actually get our hashtags into our containers. And we think a nice way to do this is by generating sample weights. So our sample weight Pik would be the probability that our node or our hashtag I gets sampled into a container from community K. And a really nice distribution for generating these sample weights is a beta distribution, because the 2 parameters, alpha and beta, give us a lot of control over its shape. We can make it, sort of almost entirely uniform, or in fact exactly uniform, or very heavily left or right skewed. We can concentrate all the density in the middle. we can push it right to the edges, although I can't imagine a situation where you'd have a community that was very strongly for and against an issue together. But we could do it if we wanted to. And it also has support over this 0, 1 interval, so it matches up very nicely with this spectrum that we're distributing our hashtags over. But of course, the beta distribution is continuous, so we need to discretize it. So it's a matter of, instead of having this continuous distribution, we want to generate m+1 probability masses that are concentrated at our m+1 nodes, that is our hashtags. And so, actually not that hard. We start with a couple of beta distributions, so we might have a red community and a blue community. They're both beta, but you can see they've got different shapes because we've changed them according to the parameters that we feed our beta distribution. But then all we do is slice them up. So we've got a set of probability masses for our nodes for them being sucked into a red community tweet. And then we've also got probability masses or sample weights for the probability of given nodes being drawn into a blue community tweet. And there is some overlap between these two distributions. And the idea is that we should be able to vary our beta parameters to make our distributions closer or farther apart as we require. So, I mean, it probably doesn't make sense to have too much overlap in the same-sex marriage debate example, but you can certainly think of cases where you'd have some communities that overlap quite closely. Maybe if you're thinking about a political system where you've got more than two parties, there'll be some parties that align on a lot of issues, and so they might start to draw together, and other parties that are sort of ideologically quite far apart, you wouldn't see much overlap between their distributions. So now we have to figure out communities for our nodes, because at the end of the day, when we simulate this projection of our bipartite graph, we'd like to be able to estimate the probability of community membership for each of the nodes or each of the hashtags in our graph. And there's no point simulating data if we don't have some known ground truth, sort of no point generating an estimate if you don't know what you're estimating. So our idea is that we should find, first of all, the center of each of our communities. And this really is just the weighted sample mean of all of our nodes. So you find a center for each of your communities, sort of the midpoint of that distribution. And then we'd assign the ith node to community K just by minimizing the Euclidean distance. So you look at all of the different communities that you've got, and the center that you are closest to determines that you're a member of that community. So again, actually not that complicated. We've got our set of nodes. We find the center for the red community. We find the center for the blue community. All the nodes that are closest to the blue center are blue nodes. All the nodes that are closest to the red center are red nodes. And we do have some mark in between to simulate where the boundaries of those different communities are. And now we need to construct the bipartite graph of U and V. So we have to sample our hashtags or our nodes into our containers according to the container sizes. So we want to fill up each container. And we sample them without replacement, just with those sample weights that we have. So if you've got a red container, you're sampling using the red probabilities. If you've got a blue container, you're sampling using the blue probabilities. And for each container that you've got, you just sample from those hashtags until the container is full. And then in our bipartite graph, you draw an edge between the ith node and the jth container if the jth container contains the ith node, or if it's been sampled into the jth container. Now, there is a risk, obviously, that this produces orphan nodes. There's a chance that in this sampling process, you'll have possibly a whole bunch of nodes that you simulated that don't get sampled into any of your containers. And I guess there are two ways around this. One is just to simulate more and more containers, or the other is to generate a larger set of nodes to begin with, so that even though you might have quite a large section or segment of orphan nodes in your final graph, the number of nodes that do appear in your graph that are connected to a community is still sort of reasonable enough to give you an informative graph or an interesting graph for analysis. So, a bipartite graph, you can see we've got our nodes that fill up our containers, but we have obviously lost some. So we've got a 0 node, a 1 on M node, a 2 on M node. 3 on M hasn't been sampled anywhere, so we jump straight to 4 on M. There's a whole bunch of other missing nodes in our ensemble, but that's not the end of the world. What we've got should be good enough. So obviously the final step then is just to project this bipartite graph over our set of nodes so that we get our simulated hashtag network. And the idea is that if we've done it right, or if we've tuned our parameters right, we should be able to get effectively whatever characteristics we want. We can get the overlap or lack of overlap between communities that we want. We should be able to get these key hubs in the network if we want them, so nodes with a very high degree. And I guess that's what we hope the model will do. I have to apologise, between the time that I wrote and submitted my abstract and appearing here, I served a 3-month internship, so work on this slowed considerably. that our hope is that we've got control over all of the characteristics of simulated graphs that we want. So we want control over edge weights, we want control over the density both within and between communities. By tuning our sample weights and the container sizes in our simulated graph, we should be able to get what we want. We've also got this idea of preferential attachment. So wherever we have a peak in our original beta distribution, that's going to produce spikes in our sample weights. So you're going to have these nodes that tend to be sampled more and more and more into your containers. And of course, by varying the distributions that we use or changing the parameters of those distributions, it should be possible to produce a network that has the scale-free characteristics that we might want for certain situations. We're also in the process of extending this to a multi-community setting. All this really requires is replacing a beta distribution with its big brother, the Dirichlet distribution, which of course means that instead of distributing your nodes evenly over a 0-1 interval, you have to space them uniformly over a simplex. This is where the method is still very much a work in process. Back on this slide where I sort of showed you quite easily how we can get these sample weights just by evenly slicing our continuous distribution. It turns out getting even slices on even two simplex, so a triangle, is non-trivial. You tend to get these problems at the edges where your areas are a little bit smaller, or these problems particularly in the corners of your simplex where you get very underrepresented probabilities. And simplicial geometry is not my strong suit, but we're getting there. The idea is that eventually using something like a constrained k-means clustering, we'd be able to get sort of a partitioning over this simplex where we have equal areas over which to integrate a Dirichlet PDF to get sort of representative sample weights. But I guess that's about it. Still very early work. Questions, comments, feedback, telling me I'm going in completely the wrong direction, absolutely most welcome. If you'd like to get in touch with me, my email is here. I should, of course, acknowledge the contributions of my supervisors, John O'Tuke, Lewis Mitchell, and Nigel Bean, and the ongoing financial and other support that I receive from two research groups back in Australia, D2D CRC and ACEMS, and of course some shameless self-promotion at the bottom in case you can't find anything better to do than read the papers that I've written so far. But thank you very much.
Each container can have more than 3 or 4
Yep.
hashtags, so
Yep.
it's a kind of hyper-edge connecting.
Yeah, that's correct. Yeah.
Yeah.
Yep.
Pieces. So did you compare with the discussion of the hypergraph?
We've begun looking at hypergraph methodology, but I can't say we're far enough to make any really interesting comments at this stage. But yeah, it's definitely an area that we need to look into further, I think.
So on this example, you have fitted your beta load to the actual data?
No, so this is really just a toy example, but yeah, I suppose the best way would be to use maximum likelihood estimation to get your alpha and beta parameters for the beta distribution for each of your communities.
Because in that case, you can give some interpretation of the cohesiveness of each group
Yeah,
of hashtag, like say.
yeah, that's right.
And this would be interesting.
More stuff for me to look into, I'm sure. No? Cool. I don't want to hold people up from coffee breaks, so please.
So what does this tell you about the Australian vote?
Um,
Any comments on that?
in regards to...
What the sentiment is on Twitter? Does that tell you anything on that?
Yes and no. So within those 6,000 hashtags, we need to do a lot of cleaning still at this stage. You get things like a really popular hashtag was marriage equality, but people couldn't quite figure out how many E's there should be between the end of marriage and the start of equality. Sometimes it was 2, sometimes it was 1, sometimes it was 4. So once we've resolved that, yeah, we think we should be able to get a fairly good sense, probably using GLASS more than this simulation method, exactly what sentiment was carried by the different hashtags, but that's also ongoing work.
Okay, so thank you very much for the talk.
Thanks.